And when we look just at the simplest parameter, simplest conceptually, temperature, what we see, and what I'm showing you here is the 2016 to 2020 difference from the 1880 to 2020 mean in temperature. And for the old records, we rely on in situ observations, measurements at ground stations, buoys in the ocean and such. So it's kind of a pulling together of different records. But for the last 40 plus years, we've had satellite observations of temperatures all over the globe. And the take home here is the Earth is pretty much warmed all over with some exceptions. And the Arctic, the high latitudes, have warmed more rapidly, you see up here, than any other place on Earth. And that gets to my own area of expertise is Arctic change. So I'm going to start with sea ice. Sea ice is floating ice. It's frozen ocean surface water, anywhere from a foot, well, inches, to 8 feet thick, maybe in some places. And it grows in the winter, shrinks in the summer, grows in the winter, shrinks in the summer. It flows with the ocean water at the margins. And what you're seeing now is growth as we approach winter. And this ice plays some key roles. It affects ocean circulation because when it freezes, it rejects salt into the ocean, which changes the density of the ocean, which sets up the global ocean circulation systems. But from a climate change perspective, ice is white and it's highly reflective. And so it has what's called a positive albedo feedback, meaning when ice starts to melt, it gets less reflective, it absorbs more energy, it wants to melt more, and so it's a self-compounding effect. So as we lose sea ice, the tendency to lose more sea ice increases. So it's an unstable mechanism, and that is in large part why we saw on this previous graph the higher warming in the Arctic. So as we then look to, I should point out, it's the satellites that orbit over the poles that observe this ice. We can understand the thickness, the spatial extent, the concentration, even the age of the ice, because older ice is less saline, and so that emits energy in a different way than fresh ice, which has more salt in it. But one thing we've done since the late 70s is track the ice extent. And you can see that in this figure here. So in September, what we call the September minimum, this is the ice as it's retreated in 1979 to its minimum extent. After September, the ice starts to grow and grow and grow and fill in more of the Arctic Circle. But we watch the ice unfold and we look at it continually at its smallest extent, and we can compare that year after year. So this is 1979. This was last September. So again, the late 70s and last September. And what your eye tells you is a significant loss of ice cover. And if we look year by year, this is the trend in sea ice. And I want to call your attention to 2007 in particular. This was a year that really shocked us. We did not know ice could disappear this quickly. Some of it flowed out the channels down to lower latitudes where it melted. Some of it melted in place, but there was a significant loss in ice cover. And I want to call your attention to the Northwest Passage in this region here. So northern Canada, between Greenland and Alaska. This is an area that's been frozen since, since humans started exploring the Arctic. And it was always kind of the gateway for commerce, because if you go back to this picture, if you could penetrate or sail through this region here, it was a much shorter route from Europe to Asia than going on the backside of the Earth. I'm sorry I don't have the image here to show you. And back in 1903, 4, and 5, guy from Norway named Roald Amundsen sought to traverse the Northwest Passage. And I said 3, 4, and 5 because it took 3 years, well, 2.5. So he set out in 1903, didn't make it in the summer, froze in, spent the winter, and then when it thawed in 1904, he sailed a little further, didn't make it out, froze in, and finally in 1905, he completed his journey across the Northwest Passage. So if we look at the Northwest Passage now, again, the area between Greenland and Alaska, we see a different world. And so in 2007, a retired hog farmer from Minnesota and his wife sailed the Northwest Passage in the Cloud 9, is the name of their boat. I think he was 76 years old and did it in 77 days. Or he was 77 and did it in 76 days, I don't remember. But I can't help but think of the spirit of Roald Amundsen looking on them thinking, you know, that's nothing. When I did this, it took 3 years. And so our environment is changing. And the way we use it, explore it, understand it is changing. And this space-based perspective is key to helping us understand how it's changing. So that's spatial extent of ice. And I'm lucky because when I speak to audiences, general audiences, members of Congress, whomever, ice is easy to understand. It's there and it's not. It's there and it's not. That's a little easier to grasp than, you know, 2 degrees Celsius of temperature change. The dramatic changes in the Arctic really are telling an important story. And we have tools not just to look at the spatial extent of the ice cover, but also the thickness. And so what I want to show you is this mission. This is something I gave both ICESat and ICESat-2. I gave about 15 years of my life to when I was at NASA. This is a laser altimeter that flies along. You can see the laser pulses that get fired from the satellite. With GPS, we know the exact position of the satellite. We know the attitude, the direction it's pointing. We know the speed of light, so we measure the travel time of the pulse to the surface below that bounces back. And from that, we can ascertain the height of the ice. And in the case of sea ice, sometimes those bounce off of ocean water, open water. Sometimes they bounce off of ice. And that allows us to figure out how thick the ice is, because 1/10 of the ice is above the water and 9/10 below the water because of the density. And so by differencing pulse returns from the water with pulse returns from the ice, we can infer the thickness of the ice. So this is a measure of the trend in, well, images of ice thickness from ICESat and CRYOSAT-2, so the predecessors to ICESat-2. And this is the trend in volume of the ice. So the thickness times the area over the couple of decades, or nearly 2 decades, that the satellites have been operational. So that's the story of sea ice. When I look at, or I want to turn now to the ice sheets, because land ice is critically important for sea level rise and the implications for low-lying vulnerable coastal communities. And what we see by comparing different measurements from the early 2000s and up through 2019, what we see here are the elevation changes. And how much, so we measure the height once, the satellite flies over it again, measures it again, flies over it year after year after year, and we get a measure of where the ice is growing, which is the blue in the interior, and where the ice is shrinking, which is the red around the perimeter. And what we have here is over the 16-year period, we've seen the equivalent of 1.4 centimeters of sea level rise lost from Greenland and Antarctica. That may not sound like much, but some of the low-lying coastal communities are just inches above the water line, inches above sea level. And Greenland has the potential to raise seas, if it were all to disappear, which isn't going to happen soon, but if it were, 23 feet. Antarctica, about 210 feet. But the question isn't, nobody expects that in the scientific community in the coming century. It's easy to see where 3 feet of sea level rise would come from. And it's not hard to see where 8 feet of sea level rise will come from. We just don't know whether it's going to be 3 feet or 8 feet. We can say with confidence the coming century will likely be at least 3 feet, but we can't rule out 8, 9, 10 feet. So that's why we're paying a lot of attention to the ice sheets. And the satellite I just showed you and a couple of others help us understand what's happening to that ice cover.